Good evening, students. So there are two objectives of today's class. First, what exactly is center of mass, and second, how to find out center of mass of discrete system of particles. So basically, we have talked about two terms. First is center of mass and second discrete system. So let's understand these two terms one by one with suitable examples. So let's get started. So first of all, we try to understand what exactly is center of mass. So pretend that there is a uniform rod is placed over a horizontal smooth surface, right? So just like imagine it to be a horizontal smooth surface, and we have placed a uniform rod over here, right, like this. So if I draw it on the board, so situation is like this. This is the uniform rod, and let's say apply a force, right, at one end of the rod like this. So what sort of motion we can expect it to be having, right? So this will definitely, the motion would be something translation as well as rotation in the clockwise sense, right? If I apply the same force at other end of the rod, now what would happen? If I apply force over here, now again this will translate, but this time rotation would be in anti-clockwise direction, right, like this, right? But if I place same force at its geometrical center, remember that it's a uniform rod. So if I apply same force at its geometrical center, it will definitely be having only translation motion. There would be no rotation in this case. So if I compare this situation where we have applied force at the geometrical center of the rod, so this behaves exactly like a point mass. Remember what used to happen in the case of point mass? So let's say if mass of the rod is m, and we have an equivalent point mass, and if we apply, imagine there's an equivalent point mass, and again let's its mass to be m, and if I apply a force over here, its acceleration would be in the direction of force, right? So a would be f by n. So similar things are happening over here. So if I apply this force at its geometrical center, this rod will behave as point mass, right? So we can assume that the that its entire mass of the entire rod can be assumed to be concentrated over here, right? And this point is known as center of mass, right? So this is how we can treat center of mass. So center of mass can be explained as that point which is inside the body as well as outside the body. I will take examples later on where entire mass of the body can be assumed to be concentrated, right? So of course this center of mass can be inside of the body as well as outside of the body. So this example is basically in which center of mass is inside of the body, right? Let's take an example where the center of mass is outside of the body. For example, suppose we have a ring over here, right? It's a ring, an entire mass, this is a ring, right? An entire mass is placed over the circumference of this ring, right? But here the center of mass lies at its geometrical center. It's a uniform ring, of course, uniform ring. And of course, there are certain ways to calculate center of mass that we will discuss later on. So if it's a uniform ring, here the center of mass is lying outside the circumference of the ring, right? So definitely it is not inside the body, but outside the body. Again, if we have an L-shaped rod, right? Again, center of mass would be somewhere here. Again, there are certain ways to calculate it. We'll see it later on. But the idea is, the central idea is that center of mass of a body can be lying inside as well as outside of the body, right? So again, I would like to repeat the definition of center of mass. Center of mass is that point inside as well as outside of the body where entire mass of the body can assume to be concentrated, right? Okay. Let's move further. Now, of course, we are we are trying to calculate center of mass of a extended body, right? It's because we are talking about rod, so of course rod is a extended system, or you might call it system of particles, which is made of infinite number of particles. Now these particles can be arranged into different ways. The first is, right, if you talk about system of particles, now there could be two system of particles. First is discrete system. So in discrete system, all the particles are separated from each other. There is no connection between two particles. For example, one particle is over here, one particle is over here, and so on, right? So there is no connection between these two particles. So such sort of system is known as discrete system. And in continuous system, like in the case of rod, continuous system, all the particles are associated with each other. For example, this rod is made of infinite number of particles, and all these particles are associated with each other, right? All these particles are associated with each other. So here we actually use integration to find out the location of center of mass. But in discrete system, we have different way to calculate the center of mass of such system. We will discuss it later on, right? But first we need to understand that we may have two types of system of particles. First is discrete system, in which all the particles will be separated from each other. There would be no connectivity between two particles. And in continuous system, for example, rod or maybe disc, right? Disc. So all these are examples of, or solid sphere, solid sphere, hollow sphere. All these are examples of continuous system in which all the particles are associated with each other or connected with each other, right? Now let's first try to find out how to find out calculation of center of mass in case of discrete system, right? So to find out center of mass of discrete system of particles, right? Center of mass of discrete system of particles. So let's pick only two particles involved in such system, and then we are going to generalize the result, right? So let's assume we have two particles, m1 and m2, right? m1 and m2, and let's say position vector of m1 is r1. So we are actually moving towards the mathematical form of how to calculate center of mass of discrete system, right? So let's say position vector of m1 is r1 and position vector of m2 is r2, right? And let's say center and let's say a force F1 is acting on this particle, right? And F2 is acting on this particle, right? So of course we can expect center of mass to be somewhere in between, right? So let's assume that center of mass is placed over here, right? And its position vector is RCM. Remember one thing, that it's not a must that at the location of center of mass there would be a mass, even though there is nothing there, but still that point can be treated as center of mass. For example, in case of ring, uniform ring, where entire mass was on the circumference but center of mass was on the center of the ring where there was no mass at all, present. So it's not a must that at the location of center of mass there has to be some mass. It's not a compulsion, right? So you can see over here there is no mass at this location, but we can assume that center of mass of these two particles are located over here, right? So RCM is basically position vector of center of mass of these two particles, right? So equivalently we might call, as individually on this particle F1 is acting and on another particle F2 is acting, so we can assume that on center of mass total force which is acting, that would be F1 plus F2, right? And here entire mass, that would be m1 plus m2, right? So what we can write, that this F1 plus F2, right, F1 plus F2, that would be m1 plus m2, and of course this would be acceleration of center of mass, right? This would be acceleration of center of mass, because we have assumed that at this point center of mass of these two particles is existing, right? Now F1 can be written as, now again this can be written as m1 plus m2 into ACM and F1 plus F2, right? So m1 plus m2 and ACM, and this would be m1 a1 plus m2 a2, because individually we are applying a force F1 on m1, so because of that there would be certain acceleration of m1, and as we are applying F2 force over here, so there would be certain acceleration a2 of mass m2, right? So ACM is how much? ACM is how much? m1 a1 plus m2 a2 by m1 plus m2, right? Now this can be written as d square RCM by dt square, right? We know that acceleration can be written as, we know that velocity is dr by dt, right, and acceleration is dv by dt. So basically, so v can be written as dr by dt, so this comes to be d square r by dt square, right? So from this logic we can definitely write this one, right? Similarly we can write m1, this would be d square r1 by dt square, m2 d square r2 by dt square divided by m1 plus m2, right? Now we can further arrange like this, d square by dt square can be taken as common, and m1 r1 plus m2 r2 by m1 plus m2, because m1 m2 all these are constant, so this can be written like this, m1 can go inside like this, m1 r1, and these are also constant, so these can be taken inside like this. Now comparing on both sides, RCM comes to be how much? m1 r1 plus m2 r2 by m1 plus m2, right? So this is for two particles, which can be generalized for n number of particles. Now there is one interesting thing. For two particles, if we talk about, the center of mass will definitely be lying on this line. I mean line joining on to these two particles. Why? We can actually prove it. How? If we arrange this equation like this, m1 r1 plus m2 r2, this is m1 plus m2 RCM, right? Now m1 r1 plus m2 r2, this is m1 RCM plus m2 RCM. Now take it to the left, m1 RCM, take it to the left. So this is m1 would be common, r1 minus RCM, right? And again take m2 RCM to be to left, so m2 r2 minus RCM. So this can also be, so this will be a null vector, so this can be written as m1 r1 with respect to center of mass. So basically this is position of 1 with respect to center of mass plus m2 position position vector of 2 with respect to center of mass, right? This can be written like this, null vector. So from this r1 cm is equal to minus m2 by m1 r2 cm. Now m2 m1, these are positive quantity, so one thing is for sure, that r1 cm and r2 cm will be anti-parallel, right? Because this is positive and it's a negative vector, so these two vectors will be anti-parallel. So what does that mean? This is what r1 with respect to center of mass. Basically this is this one vector, right? This is r1 with respect to center of mass, and this is r2 with respect to center of mass. So we can see, as these are two anti-parallel vectors, so that only means that these two vectors will be lying along the same line. So that means that center of mass will be present on the line joining these two particles, right? Now this result we have derived for two particles, but this can definitely be generalized for n number of particles. So for n number of particles, this can be written as So of course, for n number of particles, we can generalize the result. So for n number of particles, right, RCM can be written as m1 r1 plus m2 r2, and and so on, mn rn, right, divided by m1 plus m2 plus mn, right? Now this result is in terms of position vector of individual particles. This can again be written in terms of x, y, z coordinates, right? Like r1 can be written as x1 i cap, y1 plus y1 j cap plus z1 k cap. In the same way, r2 can be written as x2 i cap, y2 j cap plus z2 k cap. And if we associate all the x components together, all the y components together, and all the z components together, so the final result would be like xcm would be m1 x1. On the same pattern, we can like this, right? This would be mn xn by m1 plus m2, right? So this can be further written as sigma mi xi by sigma mi, right? I from 1 to n, and again here I would be 1 to n. In the same way, YCM can be written as sigma mi yi to n sigma mi, right? And in the same way, ZCM can be written as sigma mi zi right. So you can use either either this form or this form. Any one of the form will work for the calculation of center of mass, but I personally prefer this method, because this form, because in this particular form, you write down position vector in terms of x, y, z coordinate, and that would be easier for you to calculate, right? I will explain you with a suitable example, right? So this is general form for n number of discrete system of particles. Now let's understand how to use it in problem solving, right? So we are going to start with a very basic example, right? Suppose that we have two particles, one is having mass m and another is having mass 2m, right? So and let's say the separation of these two particles is L, right? So the first thing you're supposed to do is that you first decide the coordinate system. One thing is for sure that basically it's a two particle system, and we have already derived the result that the center of mass of two particle system will definitely be lying on the line joining these two. So one thing is for sure that this center of mass of these two particles will be somewhere here, right? Now the first step would be to decide the coordinate system. So let's pick origin at this point on one of the particle. Let's call it particle 1. Let's call it particle 1, right? And let's call it particle 2. This numbering is also important. Why? Because you are writing m1 x1 plus m2 x2. So you must be sure that you are writing x1 against m1, you are writing x2 against m2. Otherwise, there are chances of making mistakes while solving the problem. So you just assign which one you are talking, which one you have, you must be clear in your mind that which one is 1 and which one is 2, right? So let's take origin over here, and let's x-axis along this direction, right? So coordinate of this point would be 0, 0, and coordinate of this point would be L, 0, right? So definitely we are not talking about along y-axis. We are definitely talking about x-axis. But if you have to write down in terms of, let's say, position vector, so r1 would be how much? R1 is origin, so this is basically a null vector, and r2 would be how much? R2 will be Li cap. There is no there is no y coordinate involved here, right? So this can be also 0 I cap. You might write like this. So of course RCM would be, by definition, this would be m1 r1 plus m2 r2, right, by m1 plus m2. So this would be m1 is how much? M, and r1 is 0 I cap, right, and m2 is 2m, and this is L I cap by m plus 2m. So this is basically 2L by 3 I cap, right? Alternatively, if you had used XCM format, right? So if you had used XCM for calculation center of mass, in that case this would be m1 x1 plus m2 x2 by m1 plus m2, right? So this would have been m into 0 and 2m into L by m plus 2m. This is 12 by 3. So here actually these two forms does not matter, because this is along single dimension. But when we have particles where particles are kept not just along x-axis but also along y-axis, in that case, or in between maybe, so in that case it would be much easier to calculate this form, because you don't need to write again and again like xcm, ycm, zcm. You will be done with one single form, right? So I would suggest you to use this form. This would be more useful for you, right? So let's take one more example, and I think that will definitely clarify how to use calculation of discrete system, center of mass for discrete system of particles, right? So let's take one more example. So let's take three particles placed on the vertices of an equilateral triangle. So the vertices, so this is m, this is 2m, this is 3m, right, and L, right, and we have to find out center of mass of this particular discrete system. So again the first step would be to define your coordinate system. So let's take origin over here, and this is my x-axis, this is my x-axis, this is my y-axis. Now assign the coordinates of all these points. So 0, 0. Okay, again assign which one is 1, which one is 2, and which one is 3, right? So this is 0, 0, this is L0, right? And this would be how much? This is 60 degree now. So this would be how much? L sine 60 degree, and this would be L cos 60 degree, right? So this is basically root 3 L by 2 comma L by 2, right? Now RCM would be how much according to definition, right? RCM would be m1 r1 plus m2 r2 plus m3 r3 by m1 plus m2 plus m3, right? So this is m, and simply 0 I cap plus 0 j cap, might write like this, does not matter. 2m, this would be li cap plus 0 j cap, and for 3m this would be root 3 L by 2 I cap L by 2 j cap divided by entire mass, so m plus 2m plus 3m. Now simply associate all I cap, all the components along x-axis together, all components of all components along y-axis together, and all components along z. No, there is no z-axis. Of course, as there is, all these particles are placed in xy plane, so center of mass would be again in xy plane only. So there is no requirement of z coordinate, right? Z coordinate of all the particles would be 0, right? So here, if we calculate, this would be how much? So this is 2 ml I cap, and here 3 root 3 ml by 2 in I cap, and in j cap this is 0, and this is 3 ml by 2 j cap, right? 3 ml by 2 j cap. So cross check your calculation. So 2 ml, right, and 3 root 3 ml by 2, right, and here 3 ml by 2 j cap, right? So we are good. So now from here, this would be how much? This is 4 ml, so this is 4 plus 3 root 3 by 12 L I cap, and here this would be how much? This would be L by 4 j cap, right? So 4 plus 3 root 3, cross check your calculation, by 12, and this is yeah, L by 4 j cap. So this would be your final answer, right? So I hope you have understood the concept. In the next class, we are again going to discuss a new concept. Till then, goodbye.